Hey, welcome back. It's been a while. So I had a bit of a pause, so apologies to anybody who does follow the channel. We were relocating and doing some other things, so I needed to take a pause while we dealt with some issues. But we're going to get back into it. And so I haven't done any videos yet on the version 10 scriptable advanced features. So I'd like to do that, but in order to get there, what I want to do is just to maybe get back into it with a summary sheet, get an example out here, and then we can, in subsequent videos, improve them a little bit, make them a little bit prettier, fancy them up a little bit with some of those scriptable controls. So what we're going to do today is we're going to basically do a summary lesson, cover off a lot of the basics and the fundamentals, going through in a fairly short calculation dealing with two-dimensional ballistic trajectories. So I've got the problem laid out on the screen. You see the image. Again, the image. So what I will do is, as you know, I've got a lot of short videos on specific features. I'll be sure to put them down below or links to them down below so that you can follow along. So if I mention something that I don't cover in enough detail for you, you'll be able to follow that link and get to them. So we have the image, again, created in PowerPoint as a PNG with a transparent background, brought it in here. And so the problem that we're going to try to do today is we're going to say for any given initial height, velocity, and angle, so those would be our initial conditions, above the horizon, calculate the ballistic path of the projectile until it comes back to Earth or brings your Y dimension back to zero. And so the image displays that. We have our projectile up here. We have our zero as the short gray line here. We're an initial height above it, an initial velocity, and a given angle. And we'll be calculating a series of points along a trajectory at different points in time, t. So we have our initial conditions laid out. We have our initial y, our initial x, our angle, and the initial velocity. Obviously, these are all changeable for different problems of similar nature, and we can do that. So the first thing I'm going to do, I'm going to go through this, and we're just going to work through the calculation, and I'm going to annotate it as we go. And I'll try to edit it down so we don't waste too much time between important bits. So let's get started. And the first thing I want to do is, just to be clear, we're going to assume that the air resistance, sorry, where are we? Assume air resistance is negligible. Now, why am I doing this? Well, because I want it to be obvious, because it's an assumption. We should always make our assumptions apparent. But also, it kind of tweaks me that maybe at a different iteration of this same problem, maybe I want to include air resistance, and then I can get into some of those fancy scriptable controls to turn it on, turn it off, those types of things. So if air resistance is negligible, that means that our acceleration in the x direction is equal to 0. Of course, acceleration is in meters per second squared, and that should do that. So I will add in post, I'll put in all of the shortcuts that I'm using as I go along. Sometimes I'll mention them, sometimes I won't, but I will try to put them all in post. Just as a reminder as to what we're doing. So there we go. A at x is equal to 0. So we got our first little bit. Doesn't do much. And now what I want to do is I want to take that initial velocity and I want to split it into its x and its y components. Okay, so we have our velocity, initial velocity, so v sub, and that's an x, and we'll set that equal to, of course, it's the initial velocity that we started with, v sub 0, and in this case we have to use the cosine of theta to get the x components, multiply it by the cosine of theta, and of course theta is q, turn it into Greek, so we have cos theta, and then we can hit our equals, and that gets calculated out. And of course, that's for the initial conditions that we've done. We're going to do the same thing for our y. So I'm just going to copy paste, get it set up here, change it to y. V naught, in this case, of course, it will be our sine theta. And we can calculate what that is. So now we're starting to get a couple calculations going on, and I'm just going to scroll up as we go through this so that we can stay on the screen. And what I want to do is basically define as a function the x position and the y position as a function of time over the course of this trajectory. So we'll label that. So I think it was version 10, which might have been version 9, where we can now just type text, and as soon as you hit that first space bar, it will recognize that you actually want text and convert it to a text box, which is really convenient as we go along. So that's what I'm doing there. So define the position in x as a function of time. And so for this, you need to know your equation is position, velocity, and acceleration. So in this case, our position in x as a function of t, and we'll use our definition. And so it starts off with its initial position, x, and then of course what it does is it's the velocity multiplied by the time. So its initial x velocity, 0x multiplied by time, and to that we have to add 1/2 the acceleration in x times t. And you notice like we've already set our acceleration in x is equal to 0, but I'm including it here so that if we do go back and make changes here and change our assumption, that it will automatically be calculated in here. So this is what that's there. Now I just want to test my function. So let's just label that test the function just to make sure it's working. And I'll do that for each of these as we go down. And so in this case, we want to know the position, say at 3 seconds in this case. So we have to put in our units. And we get 19 meters. So seems to be working fine. So we'll just, let's move that off to the right a little bit because all that is a test. It's not necessary for the actual calculation. And so that's the position in x. Let's do the position in y. So again, I'm going to just copy those, paste them down. These are the little tricks to make it quick to get this done. So now we're going to change that to y. This is going to become y. Y at t. These become, that didn't work out so well. Back up with a couple of control Zs. Go y there. Y there. And of course, acceleration in the y, we can put in a at y or a at y, but of course that's equal to the gravitational constant. So I'm just going to put in a negative g. And because it's not defined, you'll see it'll pick up that green color, which is showing it's recognizing it as a known constant because it's built right into Mathcad. Again, I'm going to test my function, make sure it's working, make sure I'm horizontal to it, and change that to a y. And yeah, we have a position negative 1.346 meters. So obviously the overall trajectory is not going to take 3 seconds because it's below the horizon. So we're actually getting pretty close to having this solved. We're going to start to manipulate the results. But just for fun, what I'm going to do is I'm going to use a solve block to figure out at what time the projectile comes back to ground level. So we're going to put that in here. It says at what time and where does the ball land? Projectile, I've defined it as a ball here. Okay. So we put in a solve block. We can shrink it down later, but if it's too small, you can't see what the different sections are, right? So we have our guess values at the top, our constraints in the middle, and then the actual solution in the bottom. And as we get smaller, they all tend to overlap. They still work that way. You just got to make sure you put them in the right section. So you need a guess value. So in this case, everything's a function of time. So we're just going to put in time equals 2 seconds. That's just a guess. It's not intended to be the actual value. And so we have that. Now what we want to do is put in our constraints. And we want the solution for t when y at t is, oh, sorry, I need the other definition. So control equals, and we set that equal to 0 meters. So when the position in the y direction becomes 0 meters, so that's the value of t that we wanted to solve for. We can push this up here a little bit more. And then in the solution, we want the final time, and we'll set that equal to find t and hit equals. So now the solve block is doing its business, and it tells us it's going to solve or resolve the constraints at a time 2.913 seconds. So that tells us what time the ball is back. And of course, now if you want to know the position at that time, we can just go time final, set it equal to 0. We see it reaches a distance of 18.464 meters for the conditions that we started with. So we're coming right along. So the last thing I want to do, I'm going to need a little bit of space for this, is I want to basically establish a range variable of a series of points across the trajectory so I can graph the trajectory and see what it looks like. And so to do that, I'm going to establish a range variable t. There we go. We have our label. So we're just going to set it up for however number of intervals we want to define I. And so I will define the number of intervals, and I'm just going to choose 10 to start with, and we can play with that later as it'll be one of our variables. And the range variable itself is going to go from 0 to the final time divided by I. So that breaks it up into intervals, equal number of intervals, all the way to the final time. And so that's our range variable. And so I'm just going to give myself some space, go down to the next page. And we can choose x at t. And see, that's why I needed more space. See what that looks like. And we want y at t. And we can see what that looks like. And now I'm just going to introduce or draw a quick plot. So there we go, put in the plot. What do we want? We want x at t in meters, and up here y at t in meters. And if I got that right, there we go. Now I'm just going to play with my chart a little bit. And so I'll do a symbol, so I'll do the dots so we can see them. Line style, maybe dotted lines. You can choose your trace color if you like. Blue's fine. I think it shows up well. Trace thickness, maybe thicken everything up a little bit, and there we can see it. And so we have our trace, and we can see our projectile motion all laid out for us. Just get that lined up. And that's kind of what I wanted to do. So we have a solution. We have a simple problem. We've used some initial conditions, and we can change those conditions now if you want. Say if it's only going to be 1 meter, and of course we know we're going to achieve our maximum distance at 45 degrees. Maybe try that out. And if we do that, everything's gone and calculated itself, and now we're going to get to 23, what is it, 23.9 meters, and it's all laid out there. So that's it for this one. It's just a quick kind of summary recap of some of the features. I think by the time I post all this and I put in the shortcuts, it should be useful to people. If you're interested in ballistic motion, well, it'll be useful for that. If you're interested in Mathcad and the basic features, there's a lot packed in here in a fairly short period of time. And then what I'm going to do is I'm going to come back and I'm going to do some of the more advanced features. For example, we can use sliders where there's variables that we want to control between certain extremes, lows and highs. We can put in that. We can perhaps have a formatable text box which will tell us if we're hitting our target, not hitting our target. And so we'll play a little bit just to see if we can't fancy it up and demonstrate some of those scriptable controls that they introduced in version 10. So hopefully this was useful to you. Like I said, I'll put in the links below. Links to all the little videos that show in greater detail some of the features that I skimmed over in this summary lesson. So hopefully that was useful to you, and we'll see you on the next one.